Go.
Hello, my dear students, and let's finish that assignment from ChemLibre. Technically, I think it says Libre text at the top, but it's part of the ChemLibre project, joint project by National Science Foundation, University of California system that produced chemistry textbooks from high K-12, in other words, high school level, all the way through graduate chemistry. And they're all free. So whatever you do, do not buy another chemistry textbook for the rest of your life. Just use the link that I will soon post in your Google Classroom. I've yet to do it, but you can also always Google this and find it. No problem. That being said, this last question, question 5, is a little different. We're studying and looking at stoichiometry, ratios and putting things together, putting elements together so that they form an electrically neutral species and so that they go together in a natural, well-defined way in those small whole number ratios that Dalton gave us with his law of definite proportions and law of multiple proportions. And we practiced giving the name, writing the formula, and we practiced giving the formula, writing the names. And then we had another video, short video, where we solved in question 4 a series of problems where if you were given an amount, a mass, you were calculating the number of moles, or if you were giving the number of moles, you calculated the amount of mass present, or given either of those, using your mole map, you could calculate number of molecules, number of atoms, number of formula units, number of molecules. And so this is what we do. We count things because we want to know how much of a chemical we need, how much of a chemical we'll make, how much money we can get for a high value chemical, one that will fertilize plants or cure a disease or, provide us with an ore or a chemical that will make a new or better battery. We're always interested in better living through chemistry and maybe making some money on the side. That said, this last question is about determining empirical formula. This is always occasionally a chapter in a chemistry book, but usually stuck in at the different ends of chapters. In your book, it's stuck in at the end of this chapter, chapter 3, which it's called, and I'm in my copy, okay? Some of you have an AP version. Some of you have different editions, okay? But it's on page 113. It's called Calculating Percent Yield. But we also, because we want to know how much of something we make and what percent of it, for example, I have a bottle of silver nitrate. Everybody says, oh, is that expensive? I say, yes, this bottle costs $400. How much silver is in there? Well, it's silver nitrate, AgNO3. What percent of that is silver? So if I have a 1 pound bottle of silver nitrate, I don't have a pound of silver. I've got some percentage of that. And the only way to do it is to use your mole map and go through the mole. That's why the mole concept is so important. You can't make sense of anything unless you first convert to moles, okay? Always use your mole map, always go through the mole. It's at the center of the mole map too, isn't it? Our little mole, our fellow right here, this is kind of a cartoon version of your mole map, but is always at the center. The mole is at the center. You have mass and volume and number of particles around and outside it. You always see on my magnetic board the little mole. This is the mole from the American Chemical Society celebrating Mole Day, which was 10/23. So we're always going to go through the mole, but I want to show you how quickly to do this. Basically, these are the same problems, the same problem-solving strategy we just used, but we're working it in reverse. Instead of giving you a composition, instead of giving you a formula, we're giving you some data. How much is there? And we want you to work back to calculate the formula. Now, we know the formula of just about everything these days. It's a very rare new compound that we need to deduce the formula for. And so this is taught less emphasized than when I had to take it, but every book still has it, I guess, because they had to learn it, so you're going to learn it. But the other thing is, you know, it shows you how we got to where we are, because in the early days, that's what people did in chemistry. They determined chemical formulas so we could understand how these things are put together. And that's what we're doing, is working back. So we have this problem that says, give the empirical formula. Okay. What's an empirical formula? Well, it's the simplest whole number formula, H2O, for water. That's both a molecular formula, chemical formula, but it's also an empirical formula. But what about hydrogen peroxide, H2O2? That's its chemical molecular formula, but the simplest empirical formula would be HO. Because when we do these sorts of studies, we don't actually get real numbers, we get ratios. And unless we know the molar mass of the compound we're studying, sometimes it's hard to jump from the empirical formula to the actual molecular formula. So this is determine the empirical formula, which is the simplest small whole number formula. And the first question, 5A, says, I have a sample that contains 0.0130 moles of carbon, 0.0390 moles of hydrogen, and 0.0650 moles of oxygen. And tell me its empirical formula. You know, they always have one of these or two of these in the long questions at the end of the AP chemistry exam too. We're going to do this and move on. I will never ask you to do this again, but I just want you to practice it one time with me and see this. So here's what we do. Here's our process. We pick the smallest, the one present in the smallest amount. And, you know, this is that kind of thing you see in movies and TV. Here's a sample of some sludge on the bottom of this guy's shoe, and he's a murder suspect, or he's a body that turned up. What is this made out of? Or in a science fiction one, there's a planet down there, and the atmosphere has this composition. We take a sample of it. You know, can we breathe in it? Can we terraform this? Can we do something with this? Can we understand it? I take a sample of the atmosphere and I determine the percentages of what's there. And so here's a sample that had these mole fractions of carbon, hydrogen, and oxygen. So you pick the smallest, 0.0130, 0.03, 0.06, 0.0650, 0.0390. This is my smallest right here. So I set that equal to 1x, or 1. And I divide all the others by the smallest. In this case, there's two others. I divide 0.0390 by 0.0130, and it goes in 3 times. I divide 0.0650 by 0.0130 for the oxygen, it goes in 5 times. So that means in this sample, on a molar basis, I had 1 carbon for every 3 hydrogens for every 5 oxygens. Now this is a very improbable structure. I actually kind of looked it up because I figured it must be some sort of small short chain anhydride. Not anhydride, but like with an ether link between them, but I can't imagine what it really is. It's a hydrated form of a carbonate. So It has 3 oxygens involved in the structure with the carbon, and then it has water bound to it in a hydrated form. We have a lab that I want to do. I don't know what's going to happen, but where you'll determine the percent water in a hydrate of a compound. And so this was our answer. We have 3 hydrogen and 5 oxygen for every carbon. And it doesn't matter too much the order in which we do things, but biochemists always put the carbon first. Let's go on to the next one. This is somebody digs up some dirt, says, what's in it? And someone goes out and says, okay, and they see that it contains 11.6 grams of iron and 5.01 grams of oxygen. What do? Always go through the mole. Use your mole map and convert these values to moles. This first one went really fast because it was already in moles. Now this one, we're going to convert to moles. So I get my periodic table, and this 11.6 grams of iron, 1 mole of iron has a molar mass of 55.845 grams per mole. So 1 mole of iron corresponds to 55.845 grams of iron. I'm doing this so I can cancel out grams and end up with moles, okay? But if you can't remember that, use your mole map. I've got a mass in grams, and I want to convert to moles. I'm going against the arrow, so I divide my mass by my formula weight. Use your mole map. You can use your mole map on the test. When I do that, it gives me 0.2077 moles of iron. Okay? 5.01 grams of oxygen. Oxygen, this is the last time I'm going to do this, is 15.9994 grams per mole. So, again, my grams cancel. I divide the 5.01 by 15.99994 grams of oxygen. 1 mole of oxygen corresponds to that much. And that gives me 0.3131 moles. Now, what do? You pick the smallest, the 0.2077, and you divide the others by that, the 0.331. And when I do that, I get 1.5 oxygen for every 1 iron. In other words, I get 1.5x. But that, this 5x means 5 oxygens per 1 carbon. This 3x means 3 hydrogens per 1 carbon. This means 1.5 oxygen per 1 iron. They're not whole numbers. This panics students more than having giant numbers or unreasonable numbers. They're not whole numbers. What do? Well, obviously you can't have half an iron, so I double it. You might have to triple it or quadruple it, depending on how many different elements you have and what their ratios are, but this gives me something that would be 2 irons for every 3 oxygens. Ferric oxide. I'm sorry, I'm not supposed to say ferric oxide anymore. This is iron 3 oxide. Iron is +3. There's 2 of them. That's +6. Oxygen is always -2. It's group 6. Has 6 electrons. Wants to have 8. Picks up 2. Those electrons are negative. It's always 2 minus. -2 times 3 is -6. +6 and -6 balance out to be 0. This is an iron oxide ore. The other one is FeO. Iron 2 oxide. And if you get a mixture of them, you form a mineral called magnetite, a magnetic form of iron that is very common, very inexpensive, and when you mine it and chip it up and put it in a rock polisher, you make little magnets. Okay, one left. Let's get this done. So, that sounds rather, I don't mean to trivialize this. I won't say it's straightforward, but once you see the process and you follow the process, it's pretty easy. And instead of me saying, I have this many moles of iron, how many grams is it, like we were doing before, or just simply, I have this sample of iron 3 oxide, and if I have 11.6 grams of iron, how many grams of oxygen would be in it? They gave you the analysis first and asked you to work toward this formula. We don't do that a lot because, like I say, we know the formula of just about everything these days, and people use even more sophisticated techniques than gross gravimetric analysis. And by gravimetric analysis, I mean analysis by weight of samples. They use mass spectroscopy and all kinds of spectroscopic techniques that I hope Will get into too, that are much more sophisticated. Now, here's another one. This is that percentage. Gee, Dr. Shanley, what percent of that silver nitrate is silver? Well, here's a sample, and they give you percentages. 40% carbon, 6.7% hydrogen, 53.3% oxygen. Excuse me. I didn't bring my water with me this time. That is some common experimental data. This is a very common way for data to be presented in an analysis. Here's this sample we scraped off of this knife and used at the murder scene. And what is it? Well, we ran an elemental composition of it, and it was 40% carbon, 6.7% hydrogen, 53.3% oxygen. What could it be? Well, those are percentages. We need some grams, because if you look on your mole map, there's nothing to do with percentages. So what we're going to do is we're going to take this and we're going to assume we started with 100 grams of sample. So I started with 40 grams of carbon in that 100 gram sample. 6.7% of the 100 grams was hydrogen, or 6.7 grams, and correspondingly 53.3 grams of oxygen. I told you that was the last time I'm going to do that. Carbon is not 12.01104, whatever it says in our periodic table. I'm just going to call it 12, okay? And I have 40 grams of carbon. Using my mole map, I convert to moles. Always go through the moles, and you'll be at least on the right path to solving your problem. Convert to moles. Because it's in moles, but use your mole map and dig your way out. But no matter which way, what you're looking for, mass in grams, volume in liters, number of particles, you need to go through the mole. So here's 40 grams of carbon. 1 mole of carbon weighs approximately 12 grams, 11.9994, something like that. But this, or 12.01015 or something like that. I forget exactly what it is, but it's 12. And if I do that, I get 3.3 moles of carbon, okay? And then, if I do the hydrogen, of course, hydrogen is 1. You can look on your periodic table and see that, hydrogen is really 1.00795. I promise you, those digits way out there, 3, 4, and 5 places are not going to become important to us. And when we do that, we get that 1 mole of hydrogen is 1 gram. That this 100 gram sample has 3.3 moles of carbon, 6.7 moles of hydrogen, and oxygen. I'm just going to call it 16, not 15.9994. And I'm not going to give this any more exposition this year or in the future. It's 16 for our purposes. But that would correspond to 3.3 moles. You see those ratios? I don't think you need to divide each one of them by the smallest one, which is 3.3, because this is 1 to 2 to 1. 1 carbon, 2 hydrogens to 1 oxygen. So our empirical formula is CH2O. And this sample is probably a carbohydrate. For example, glucose. Everybody knows glucose from your biology, photosynthesis, blood glucose. It's our beginning of glycolysis and our respiration. It's fundamental to all life, and it is C6H12O6, but its empirical formula is CH2O. In fact, that's where sugars got the name carbohydrates from, because they all have the empirical formula CH2O. Carbo for carbon, hydrate for hydros or water. It's not hydrogen. In this case, it's hydros, the Greek hydros for water, because you know also when you burn these, you give off what? In the presence of oxygen, CO2 and water. You can fog a mirror because there's water coming out not from the water you drink, but from the sugar and the foods you're burning, and of course carbon dioxide because you are metabolizing them. So those are your solutions. That's your lecture over determining formulas, percent composition, and empirical formulas. And we will move on in the next video, which I'll get posted as soon as I can, and re-examine the stoichiometry in that balanced equation from the sample final exam. In the meantime, let's consider this another assignment, hand it in, I'll grade it and get those grades. If not posted, returned to you and ready to be done. So, stay safe, and I'll see you in the next video. Goodbye now.